So with weak acids and weak bases, we're dealing with equilibrium, we are dealing with K values, and therefore we are dealing with Rice tables. So right here, I wrote the same ionization reaction for hydrogen ion, but leaving out the water. So I just have H plus instead of hydronium. Both are very common and totally acceptable. And both get the idea that the concentration of my ions over the concentration of my unionized acid is what my K is equal to. And when we turn that into a Rice table, the nice thing with weak acids and weak bases is we get into a pattern with lots of similarities. So as we look at it right here, we're given a molarity of our acid, and we assume relative to that that we have no hydrogen or none of the other ion unless we're told differently. Well, some of this ionizes to make those ions. So then we have a molarity, a tiny bit of which has been ionized, and it has turned into our ions. So as we're looking at this, a nice thing is that whether it's an acid or a base, whether it is monoprotic or polyprotic, the ionization happens one hydrogen ion at a time. So this row is always the same, minus X, plus X, plus X, which allows us to kind of predict and know what's going to happen in our Rice table. That also means that over here it's X and X. So the top of our equilibrium expression would always be X squared. And the bottom is the molarity minus however much has ionized. But because these are weak, in almost all cases, we can think about what that means. The amount ionized relative to the initial amount is very, very small. So we ignore the minus X on that. Your textbook has great examples proving how this ends up the same whether we do our minus X or not, which is great to see. And if you're looking at equilibrium in college, sometimes you do have to solve for the minus X, or you need to be able to prove and check that the minus X simplification isn't necessary. We don't have to be able to prove that. But we can know that this is probably going to work if our molarity is more than 100 times bigger than our Ka. And if you want proof or the math that supports that, check out your book or ask me about it. But as we're doing that, we said there's other things that we know. X and X is always on top, and that means our X is equal to our hydrogen ion or hydronium ion concentration. And that is related by the equations we just saw to the pH. The negative log of X is equal to the pH. pH to 10 to the negative pH would then be equal to the hydrogen ion concentration. So all of this allows us sometimes to shortcut or to simplify our Ka expression, that it's X squared over the initial molarity is what our Ka is. And in problems, sometimes we're given Ka an initial molarity. We can solve for hydrogen ion concentration. Sometimes we're given pH and we plug that right in for our hydrogen ion concentration so we know what X is. And if we know what X is in Ka, we can solve for initial molarity. Or if we know what X is in initial molarity, we can solve for Ka. Those are the three variables we're looking at. With weak bases, the equation looks similar. We have X squared over the initial molarity is equal to our Kb. The only difference there is remembering that the X is equal to hydroxide ion instead of hydrogen ion. So you do have to pay attention if you're asked for pH or pOH. You do have to pay attention if your X is the hydrogen or the hydroxide as we're looking at acids and bases. And sometimes as we move through a problem, it'll go from one to the other. So in the practice problems, I do several of these by showing the Rice tables, and some of them by kind of skipping it, and jumping straight to the K expression. Both are really good to look at, to see, and to become experienced with, because you're definitely going to see a lot of math like this in both multiple choice and free response for acids and bases.